Today, we're going to follow the incredible invisible journey of a Wi-Fi signal.
I mean, we use it every single day, right? It's just there. But have you ever really stopped and wondered how it actually works? How does that video, that email, that game just magically fly through the air from your router to your phone? Well, today we're going to follow that signal on its wild adventure.
Every great story needs a beginning, and for our Wi-Fi signal, it all starts here. A signal is born. You could call this its call to adventure. So, at its absolute most basic, a radio signal is just raw energy. The best way to picture it, think of the sun. It just radiates light and heat in every single direction all at once. It creates this perfect sphere of energy. That's kind of our starting point. It's powerful, sure, but it's also really, really inefficient if you're trying to send that energy to one specific spot.
Now, there's a fancy technical name for this perfect sphere of energy. It's called an isotropic radiator. And honestly, it's just a theoretical idea. It doesn't really exist in the real world. But it's super important because it's the perfect baseline, the 0 point, that we use to measure all real-world antennas against.
Okay, so if our signal starts out as this giant, unfocused ball of energy, how in the world does it get where it needs to go? Well, this is where our hero finds a guide. This is how antennas find their focus.
See, real antennas are the solution to our problem. Their entire job is to take all that raw energy and give it shape. They don't create more energy. They just take what's there and focus it, kind of like how a magnifying glass focuses sunlight into a single powerful beam. They point the energy where it needs to go. And how do we see this focused shape? We use these things right here. They're called polar charts, and they're basically maps of the signal's energy pattern. We get to see it from two different angles, a side view, which is the vertical pattern, and a top-down view, the horizontal pattern.
Just to make sure we're all on the same page, that top-down bird's eye view is called the azimuth. And the side view, which shows us how high or low the signal is going, that's the elevation. You put them both together, and you get a pretty good 3D idea of where that signal is headed. But here's where it gets a little tricky. There's a detail here that trips almost everybody up. You see, the scale on these charts is logarithmic, not linear. So what on earth does that actually mean? It means that the shape you see on the chart is not a literal map of the Wi-Fi coverage. Check this out. On the left, that's the standard chart we all see. But on the right, that's what the signal's strength actually looks like in the real world. That big, round, friendly-looking shape on the left is actually a much longer, much narrower beam in reality. The chart is totally deceiving.
Okay, so our signal is born and it's been focused by an antenna. But now it has to face the real world with all its obstacles. Welcome to the next and most perilous part of its journey, the road of trials.
Now, you might think a Wi-Fi signal travels in a perfectly straight line, like a laser beam, but the truth is actually way cooler and more complicated. The energy really travels in a sort of invisible football-shaped area called the Fresnel zone. And for that connection to be strong and stable, this entire invisible football needs to be kept clear. And here's the rule of thumb. If an obstacle, like a big tree or a wall or a building, blocks more than 40% of that invisible Fresnel zone, your Wi-Fi link can get really unstable or even drop completely. It's not just about what you can see in a straight line, it's about that whole invisible space.
There's another invisible challenge too. It's called antenna polarization. Basically, it's just the orientation of the radio waves themselves. Are they moving vertically, up and down, or horizontally, side to side? The best way to think about it is like a secret handshake between the two antennas.
And that leads us to the golden rule of polarization. And it couldn't be simpler. For the best possible connection, the sending antenna and the receiving antenna must have the same polarization. If one is vertical and the other is horizontal, that secret handshake fails and your signal quality just plummets.
So, after all these challenges, you might be thinking it's a miracle we get good Wi-Fi at all. But luckily for us, modern technology has given our signal some amazing new powers to help it not just survive, but actually thrive on its journey.
In the old days, we used to have something called simple diversity. It was okay, it used a couple of antennas, but it would just listen with all of them and then pick the one single best signal it heard. It's like having two ears, but only listening with one at a time. But modern tech, it's called MIMO, and it is a complete game changer. It uses multiple antennas to send and receive multiple streams of data all at the same time.
So what are MIMO's superpowers? Well, it uses all its antennas at once. It can cleverly take signal reflections, which used to be a huge problem, and actually use them to make the connection stronger. It can even use different polarizations on purpose to create totally separate lanes for data to travel on. And the result? A massive, massive increase in both speed and reliability.
So our signal is now focused, it's navigated all the dangers of the real world, and it's been supercharged by modern tech. We are at the final step of the journey, the final connection. This is where the signal meets the physical hardware.
First up, we've got the RF cable. It's pretty straightforward. It's the physical highway that carries our precious signal from the radio, which is inside the router, to the antenna itself. It's simple, but it's absolutely crucial. And connecting that highway at both ends are the RF connectors. These are the critical final links in the whole chain. And as you can see, they come in a ton of different shapes and sizes. You have got to get this part right, because using the wrong one is like trying to use the wrong key for a lock. It just won't work. No connection, period. But wait, there's one more invisible property we have to get right. It's called impedance. It's a measure of electrical resistance. And here's the deal. Every single piece in the chain, the radio, the cable, the connectors, the antenna, all of it, has to have the exact same impedance. For Wi-Fi, that's 50 ohms. If there's a mismatch anywhere, the signal literally bounces backward, which wrecks your connection.
And one last thing. For any antennas that are mounted outside, there is a vital piece of safety equipment called a lightning arrestor. It sits on the cable line, and its job is to protect all your expensive indoor gear by taking the huge electrical surge from a nearby lightning strike and safely sending it into the ground. It's a tiny device that can save you from a huge disaster.
So, as we've seen, that little Wi-Fi signal that you're using right now is on a truly epic journey, from an unfocused ball of energy to a supercharged data stream that has to navigate a world full of invisible obstacles. It kind of makes you think, doesn't it? Are you giving your signal a clear path to complete its journey?